denotes the software cost of VI. So C function X indicates communication cost, in which Cij denotes communication cost between Vi and Vj if the two nodes are in different contexts. Hence, the hardware cost, software cost, and communication cost of problem P are formulated as these are the formulas. So dispersion correction in strategy. Uh, for the hardware software partitioning, it is also concerned to find an effective penalty function to handle with these invisible individuals. However, penalty function-based method does not change the nature of invisible individuals. So when node I is assigned to software component, the sum of communication costs of all its adjacent nodes assigned to the hardware are given as this formula, where C old is equal to the summation of Cij. And if the node I is corrected, the sum of communication costs of adjacent nodes is changed as well. So after it is changed to implementing on hardware component, there will be communication costs between all its adjacent nodes assigned to software components. The sum of communication costs of VI becomes this. So delta Ci denotes the change of communication cost of node I. It is obtained by the following formula, where delta Ci is equal to C old minus C new. Combining delta Ci with the hardware cost and software cost of node I, we select the node assigned to software component, the minimum ratio, and set it as 0. At each step, only one node is corrected, and the hardware cost Hx, software cost S, and communication cost C are updated. The procedure does not stop until the hardware-software partition satisfies the constraint as shown in algorithm 1, that is a one-step correction, where the input is a task graph G, constraint is R, and hardware-software partitioning X, and the output is a corrected hardware-software partitioning X. So this shows you the one-step correction algorithm. So after the first correction, the under constraint individual becomes visible. In order to optimize its solution, it is further corrected by setting the nodes assigned to hardware component as the one implemented on software component. This process is called intensification correction. So algorithm 2 shows you the intensification correction algorithm, where the input is a task graph G, constraint R, and hardware software partitioning X in the first correction, and the output is hardware software partitioning X of two-step correction. So this algorithm here shows you the intensification correction. Now we go to the next slide. Genetic operations for hardware software partitioning. So at each generation, standard genetic algorithm selects two individuals in the current population as parents. The algorithm either passes as parents directly to the new population or generates two offspring individuals from the parents. Hence, how to select the two individuals from current population is an important issue. The Rowley wheel selection cannot handle a minimization problem directly. So in our problem, the goal is minimizing the hardware cost. For hardware software partitioning, the smaller the hardware cost, the more the saved hardware cost. We rub the Rowley wheel selection based on saved hardware cost. The individual with more saved hardware cost has high probability to be selected. Meanwhile, the probabilistic characteristics of Rowley wheel selection makes individuals with small saved hardware cost have a chance to be selected. However, it is possible for the same individual to be selected again as a parent individual if directly using Rowley wheel selection twice. To overcome the shortcoming, we propose a random sampling and combine it with Rowley wheel selection. The formula for the random sampling is given as follows. Here, to generate the new individuals, standard genetic algorithm generates offspring individuals either by crossover operation to combine the vector entries of a pair of parents, or mutation operation to make random changes to a single parent. So this figure over here shows you the crossover based on component. Uh, the crossover operation is performed as follows, as shown in the figure. For each component in the parent individual, so every two of them are swapped. After that, two new individuals are generated. The update strategy is after the genetic operations, a new population is created. It is noteworthy that genetic operation only generates the solution vectors of individuals. So next, the hardware cost, software cost, and combination cost of each new individual are obtained according to the formula that was shown in the previous slide, uh, 4 and 6, h of x and z of x. Uh, this process of genetic operations does not check whether the new individuals satisfy the constraint or not, resulting in under-constrained individuals in the new population. Uh, Dispersion correction is utilized to make the infeasible solutions feasible. The old population is replaced with the new population. Meanwhile, an individual with the optimal hardware cost is obtained. If this hardware cost is better than the global hardware cost, then updating the global hardware cost. So now we come to the algorithm complexity. Sorry. At each iteration for each individual, the complexities of computing costs is uh, O of n square, which means the worst case is dominated by computing the communication cost. At the stage of dispersion correction, the time complexity is O of k star n plus m. The time complexity of genetic operation is O of m, capital M into n, in which m denotes the individual number, that is capital M. Therefore, the overall time complexity at each iteration is O of m into n square plus k into n plus m. So now we come to the CPU GPU parallel strategy. So the first point is highly efficient parallel approach for enhanced genetic algorithm. On one hand, modern personal computer systems consist of multi-core CPU and many core GPUs, which form a heterogeneous computing platform. So how to combine advantages of both CPU and GPU to solve real-world applications is challenging. Whereas on the other hand, most of exciting methods for hardware software partitioning focus on sequential implementations which do not leverage the available computing resources on personal computer systems. So based on the above enhanced genetic algorithms which with dispersion correction of hardware software partitioning, the section devises a highly efficient parallel approach for the algorithm which addresses several key issues. The first one here is how to parallelize the algorithm components. The second one is how to map these algorithm components on CPU GPU. The mapping should match well the architecture of the CPU GPU. The third one is how to transfer data between CPU and GPU efficiently. Therefore, we present a parallel genetic algorithm with dispersion correction for hardware software partitioning, in which the individual processing are run in parallel on CPU and GPU. We present a CPU GPU parallel strategy to take the advantage of the parallel power of both multi-core CPU and many-core GPU. The proposed strategy computes the costs of each individual in parallel on CPU and corrects the under-constrained individuals in parallel on multi-core GPUs. So the second point is computing individuals' costs in the way of data parallel on GPU. So in our method, the GPU will be utilized to compute each individual's hardware cost, software and communication cost, and in order to perform the truth level selection, GPU will also be used to calculate the hardware cost of each individual. Although the thread running on GPU is a basic unit, as we know, the thread is a basic unit, and one thread can be mapped to one individual logically. However, this configuration has following drawbacks. So the drawbacks are number one, the number of individual and genetic algorithms is generally less than that of arithmetic units on modern GPU. Therefore, this configuration does not leverage the available computing resources of GPU. The second drawback is, furthermore, this configuration the second drawback is that this configuration fails to make fully use of the data parallel characteristics. So in our method, a thread block is mapped to an individual and the intra-block threads are mapped to the genes of an individual. For hardware software partitioning, a gene of individual represents a partition of a node in a task graph. So figure 6 shows you the difference between the process of standard reduction and that of computing hardware costs for hardware software partitioning. For computing the software cost and the saved hardware cost, they follow the same way as computation of the hardware cost. Whereas the computing communication cost is quite different for above computation methods. For each individual, the efficiency of computing the communication cost depends on the representation of task graph of GPU. It is noteworthy that the weight on each edge denotes communication cost between a pair of nodes if they are in different contexts. The original formula 6, as we had seen, this formula of, of communication cost. The task graph is represented as an adjacent matrix in which the complexity of sequential procedure of communication cost is O of n squared. The third point is multiple CPU-based dispersion correction of invisible individuals. After each new individual obtains a hardware cost, software, and communication cost, the feasibility of individual will be checked based on constraint R. If an individual does not satisfy the constraint, a dispersion uh, correction strategy will be invoked. However, the process of dispersion correction inside algorithm 1 and algorithm 2 are extremely irregular. Firstly, at each iteration when the two algorithms stop depend on how far the under constraint individual is away from the constraint. Secondly, for example, of algorithm 1, line 2 to line 5 are the mean procedures, but the number of loop depends on the number of nodes assigned to software. And lastly, in order to correctly realize the two algorithms, two data structures of managing the partition nodes are created, and the data structures accessed frequently the whole procedure. The same data structures are also used in the algorithm 2. So therefore the section proposes a multi-start strategy of parallel dispersion correction on multiple CPU for the algorithm with the following two reasons. The first reason being the irregular dispersion correction processes inside each individual is more suitable for CPU than the GPU. And the second reason, furthermore, for overall individuals, the processes of dispersion correction are independent of each other, meaning that they can be parallelized. Multi-start of correcting the under constraint individuals can be accelerated by multiple CPU. So the fourth point, an asynchronous transfer pattern overhead. So this figure that you can see here is the asynchronous transfer pattern between data transfer and kernel execution. In order to further improve the efficiency of proposed algorithms, we proposed an asynchronous transfer pattern. This for CPU and GPU computation, in which the processes of data transfer and cost computation run in way of pipeline. This we can minimize the transfer overhead. So the proposed flowchart of CPU parallel genetic algorithm with dispersion correction strategy for hardware software partitioning is shown in this figure. So this is the flowchart. Okay, so finally we come to the conclusion and the future work of this IEEE research paper. So as we saw in this research paper, this paper presents a CPU-GPU parallel genetic algorithm with dispersion correction for hardware software partitioning. The contributions of this work are as follows. Firstly, an enhanced genetic algorithm with dispersion correction is presented. The under constraint individuals are marched to feasible region with dispersion correction step by step. Secondly, the individuals processing including costs, computation, and dispersion correction are run in parallel. For a given problem size, the overall running time can be reduced while keeping the diversity of genetic algorithm. Thirdly, we present a novel parallel strategy by leveraging the parallel power of multiple CPU and that of many core GPU. The proposed strategy computes the cost of each individual in parallel on GPU and corrects the unconstrained individuals in parallel on multiple CPU. Fourthly, in order to further improve the efficiency of the proposed algorithm, we propose an asynchronous transfer pattern for CPU GPU in which the transfer process and computation process are overlapped and eventually the overall runtime is reduced further. The above technical details and strategies have two benefits. The first benefit is the intensification of exploitation is enhanced while the diversity of exploration is maintained, and the second benefit is an efficient parallel approach is constructed to match well the architecture of CPU GPU hardware to greatly reduce the runtime when considering the computation workload for improving the solution quality. Numerous experiments demonstrate the effectiveness of the proposed approach. It's also very interesting that the proposed ideas have general significance to guide how to accelerate other types of hardware software co-design as well as other applications in CAD and graphics, computer supported corporation work, image and video processing. So with this we come to the end of our research paper. Thank you. This is Rolano Rebelo.